Hi, this is Tim Malloy with video 4-2 on oscillation. I'll be covering a problem from WebScience C. So let's get started. An 86 kilogram bungee jumper steps off a bridge with a light bungee cord tied to her into the bridge. The unstretched length of the cord is 15 meters. The jumper reaches the bottom of her motion 39 meters below the bridge before bouncing back. We wish to find the time interval between her leaving the bridge, part 1, and her arriving at the bottom of her motion. Part 2. Her overall motion can be separated into a 15-meter free fall and a 24-meter section of simple harmonic motion. Before we get into the questions, I wrote these two parts out. So you have first your free fall, which is the cord has slack in it. It's not stretching. Sorry. And then you have your oscillation where the cord is stretching. That's a pretty simple concept, I think, and some good foundations to get before we jump into things. Okay, for part A, they ask us what is the appropriate analysis model to describe her motion for the free fall part. So part C is correct. It's a particle under constant acceleration because simple harmonic motion, we're just thinking of things as particles and not like the system with center of mass and all that stuff that we learned about this year. And we know from physics honors that constant acceleration is considered free fall. And then part B asks us, well, what is the time interval she was in free fall? Again, simple kinematics from last year. We know that the displacement during free fall is 15 meters. We know that the acceleration to the gravity is negative 9.8 meters per second squared. So we need to find time, and we are only left with position and acceleration. So first we're going to find velocity in this equation, and then we will be able to plug it in here to solve for we're going to find velocity here, and then we'll be able to find time here using the velocity. Okay, so then we set v squared equal to 2 times negative 9.8 meters per second squared, and times negative 15 meters. Solve that, we get 706 meters per second. I chose not to put that on a decimal just for whatever reason. No specific reason, I guess. And then we have 706 meters per second equals 9.8 meters per second squared times time. Time equals 1.75 seconds. We check that out. It is all good. And then we move on to part C, which asks, for the simple harmonic oscillation part of the plunge, is the system of the bungee jumper, the spring, 1, 2, 3, and the earth isolated or non-isolated? Isolated is correct because isolated system implies that energy and momentum are conserved, and this is a true statement for simple harmonic motion. Okay, so now we have part D, which is getting into the oscillation. We've got to lock in, I guess. That's what I wrote. And so from your response in part C, which is isolated system, find the spring constant of the bungee cord. So response in part C, that was about the system, energy. Let's use the system given in part C to solve for energy. I'll get into these three givens later, but I'll just explain the flow diagram first. So at the start of oscillation, which is after the 15-meter free fall, we have some kinetic energy from all that speed she gained, and some gravitational energy because she is still above ground. There's no elastic energy because it's the instant right before the spring begins to stretch. And then we move on to this other point in time I chose, which was when the cord is tense at the ground. Everything's an elastic energy. We're at the ground, so there's no gravitational energy. We're not above it or anything. And then there's no kinetic energy because at the maximum point of in equilibrium. So when position is maximum, I guess position away from equilibrium in this instance, the velocity is 0. So then we create an equation out of that, k equals 1/2 mv squared, gravitational energy, mgh, all that. And then we plug in our givens, which I'll now explain. So we know mass equals 86 kilograms, and then our amplitude equals 24 meters, which is just the total distance above the bridge minus the distance covered by free fall. And then Vmax, which again, start of oscillation, V, that velocity, the speed is maximum, equals to 706 meters per second. Plug all those good values in, solve for spring constant, and spring constant is equal to 114 newtons per meter. So that was pretty good. That was a big part for me to be able to get that, and I'm happy it all worked out. So now on to part E. What is the location of the equilibrium point where the spring force balances the gravitational force exerted on the jumper? So the key in that question was where are the forces equal, basically. Just simple free body force diagram. I guess it doesn't really mean much, but you can understand what I was trying to get. I think that was an inappropriate advertisement. No, it wasn't. Okay. So where does tension force equal gravitational force? So we plug in spring constant times position equals mass times gravitational acceleration, plug in our values, and then we get position equals 22.38 meters. So we are, this is quite the big problem, but we're almost finished. What is the angular frequency of the oscillation? Angular frequency equals root spring constant over mass. We know that. We also know this. That's all good. 1.15 radians per second. Rather simple. And then what is the time interval required for the cord to stretch by 24 meters? So they're basically asking us, you know the time from when she's in free fall. We know that, so that's good. But now what about the time? Well, how long does it take for her to get from, I suppose, the beginning of oscillation to not the end, but I guess when position stops increasing. And that is unknown. So I went ahead and wrote the standard equation for position in a simple harmonic motion, except I opted to use sine instead of cosine. So we're going to use sine, and we're going to call the starting point 0 meters. So I guess you plug in time equals 0, and then your position is at 0, but you're 24 meters above the ground. No, I mean you are, but in this instance, I just decided to call it a point of reference. So any more distance that we travel is going to be negative. It's not a whole big deal. Actually, it's not negative. I chose not to make it negative, but that's besides the point. So amplitude equals how far the cord stretches, 24 meters. X equals, or position equals distance we're finding, which is 24 meters. Again, they asked for 24 meters. So then plug in 24 here, plug in 24 here, plug in 1.15 radians per second. I'm sorry I misspoke and I said this is going to be negative. It's not going to be negative. And so that would give us negative time, which is not really what we want. So then time equals 1.36 seconds. And then part H just asks for both times added together. And then that gives us the answer to the final question, 3.11 seconds. Here are my takeaways. It's key to know where velocity, position, etc., like energy, acceleration will be at their min-max in oscillation. We spent a whole lot of time about that, so you really should, understand, commit those to memory, write them in your calculator if you must. And just because gravity does not affect a simple harmonic spring oscillation does not mean there's no gravitational energy. So just thinking about back to the lab 1-12, my group had we had the pendulum, and gravity does affect that kind of oscillation. But with this spring, bouncing back and forth, nope, gravity does not affect it. In a simple harmonic oscillation, that's important to know, or important to remember, like what kind of oscillation you're looking at. So again, just because it doesn't affect it doesn't mean there's no grav energy, and that gravitational energy helped us find the spring constant in part, not D, part, wait, no, yeah, it was part D. Okay, so that's all done. Thank you for watching.